This is a light lecture. Light is our most important tool. Without light, we don't have any pictures. The word photograph is Greek in origin. It means to write with light. Sunlight is our most common light source that we use to take pictures. Light is a part of the electromagnetic spectrum. The electromagnetic spectrum is measured in meters and down to nanometers, which is a billionth of a meter. Light travels at 186 miles per second. A very small part of the electromagnetic spectrum is light. It's from 400 to 700 nanometers. If it's not visible, it's not light. If it's a part of the electromagnetic spectrum, but it's not light. One of my pet peeves in life is people who talk about ultraviolet or infrared light. Neither one of those are visible. Ultraviolet you can't see at all. It makes other things fluoresce, brings them into the visible spectrum. And infrared is heat. It's not light. It's a part of the spectrum, but it's not light. So here is a representation, illustration of the electromagnetic spectrum. It's from cosmic rays to broadcast band, and it goes again ultraviolet. You start seeing purple, and then up at the top end is infrared, and it's no longer visible. It's heat. The shortest part of the visible spectrum is 400 nanometers, the color violet, and the longest is 700 nanometers. This is an example, a real-world example of how light is made visible. We have white light coming through a prism, and then it is separated into all the colors of the visible spectrum. You can see on the far left the red, and then where the red and green come together, you get yellow. You go red, yellow, green, and then you go the green to blue, and then on to purple, violet. The three primary colors of transmitted light are red, green, and blue. And equal amounts of these lights produce white light. That is shown in here. All of the colors come together, and it produces all of these parts of the spectrum. They're red, green, and blue there. This is another illustration showing the same thing. We've got individual light emitters of red, green, and blue light. Where they overlap, they produce red and green produce yellow, green and blue produce cyan, and red and blue produce magenta. Where they all come together, they produce white light. Here is the example of this in nature. The rainbow is separating the white light into its visible parts. In photography, we have something that we use. It's called Kelvin temperature. It's the color of the light that is out there in nature, and or we have created using other sources to produce light. At the very low end of this, you have 900 degrees Kelvin. These things are called black body radiators. They're made out of carbon. And what happens is the light comes in through the top of one of these, and you see inside, when you put these in a blast furnace and you heat them up so that they change color. At 900 degrees, they're not ruby red. At 1750 degrees, they're yellow. And at 3200 degrees, they get kind of orangey. And at 5500 or 6000 degrees, they get blue. So the light changes color. The higher the Kelvin temperature, the bluer it gets. The lower it gets, the Kelvin temperature, the redder it gets. Here are real-life examples of Kelvin temperature. A candle is about 1,000 degrees Kelvin. Sunsets and sunrises are about 2,000 degrees Kelvin. And then you get up, we had what were called photo floods. They're about 3,200 degrees Kelvin. Then we have an electronic flash unit. It produces daylight up somewhere between 5,000 and 6,000 degrees. Bright sunny days are about 6,000 degrees. We can control this in our cameras. We can control how we want to capture these images. We see the picture and we can adjust it to whatever we see or we want our audience to see in the pictures. Incandescent light bulbs are going out of fashion. They are very efficient at producing heat, but terribly inefficient at producing light. They cost a lot of money to operate, and they generate a lot of heat. LED lights produce a very small amount of heat and are very efficient, and they last a very long time and produce light much more efficiently. The cost of an LED light will go down as we produce more and more of these. LED lights cost a fraction of what it costs to operate a incandescent bulb. And again, the incandescent bulb produces heat. The light bulbs, LEDs, will last for years. In my home, I have taken all the incandescent bulbs out and replaced them with 6,000 degree Kelvin LED lights so that it looks like daylight inside of my home. This is subtractive color theory. This is what we do when we're printing something on a page. You might remember or see these. These are the colors of your inks in your color printer. It's called CMYK, cyan, magenta, yellow, and black. We use these to produce full color pictures, copies from your printer in your home. When you're doing this, the light comes and strikes the dot, and it reflects the color and absorbs the other colors, the red, the green, and the blue, or in combination, cyan, magenta, and yellow. You can produce every color in the spectrum using these little dots, and you overlap them to create these dot images. And here's how it works. Dot matrix printing. You put down cyan, and then the magenta, and the yellow, and the black. You can produce black by overlapping all of these colors, but then you use up 3 different types of ink, and it's a muddy black, not a really true black. So it's much more efficient to use them for color production rather than black production. Here are examples showing how using the dot matrix printer works. You overlap the little dots and it produces a full color image. Light and reaction. A reflective surface, when you're taking pictures of a mirror or chrome or some type of flatware or something, you aren't taking pictures of the object, you're taking pictures of what is being reflected in the object. You need to be very, very careful when you're taking pictures of reflective surfaces. When you're taking pictures of dirt or paper or something that is porous, it absorbs the light and it just flattens out. Refractive, that is something like glass or water that allows the light to travel through it and redirect the light so that it doesn't go in straight lines like we're used to. Smooth surfaces, the law says the light reflects off the object at the same angle as it goes in. So if you're taking, when you're taking pictures of a mirror or a highly polished surface, you need to be very careful and realize that the angle of reflectance is equal to the angle of incidence. So again, the light goes out at the same angle that it goes in. If you've got a rough surface, piece of paper, dirt, some other regular surface, it's reflected in multiple directions. Again, this is an illustration showing the angle of incidence and the angle of reflectance. Be very, very careful when you're taking pictures of a shiny object. This is not a picture of your instructor. This is used for demonstration purposes, and I caution you to be very careful, because I needed to get your attention and let you see that you need to be very careful when you're taking pictures of reflective surfaces. And this is refracted light, so when you are out there fishing or you're looking at something that the density of the water or the glass are different than and the light travels differently than it does in air. It doesn't travel in straight lines anymore. This is what happens when you have glass and water. It redirects the light and it goes in different directions, unpredictable. The inverse square law. If I teach you nothing else in this class, I think this is one of the most important things that you will learn in my class. And it is light falls off light intensity decreases Light intensity decreases inversely proportional to the square of the distance. Let's put that into English. That means that instead of you starting out with 100% of your light at 2 feet, you would think that you'd have half the light that you started with. You don't have half, you have 1/4. So it's 2 times 2, 1/4. At 3 feet, you don't have 1/9, you have 1/3. At 5 feet, you don't have 1/5, you have 1/25. So whatever you've got for a light source, usually electronic flash, and you're taking pictures at night out at a crime scene, the absolute maximum that you can figure that your light source is going to reach out and illuminate your scene is 10 feet. Because what do you have at 10 feet? You have 1/100th of the amount of light that you started with.
Quick question. The actual equation, do you want me to put it up there?
Yes.
Okay, because I believe it would be 1/x². If I'm not mistaken. Okay, I'll put the equation in there for you.
Here's the real world example of how it works. You can see that the light, you've got a bright foreground and it's well lit, but it decreases very, very quickly off into the dark sky. We're going to talk about this later on, but notice that there are lights in this scene that are available that you could use to illuminate your crime scene, and that using a flash unit might not be your best choice to document a crime scene like this using a flash. Here's my example. I did this at home. This is a picture. It's showing on the left, showing the reach. We got tire transfer on asphalt here with a flash, and you see how far it goes. And on the right side, I took this picture using available light. Nothing changed other than I used a long exposure and there was light available, and I made these 2 different exposures, one with flash and with available light. A gray card. A gray card is your friend. A gray card is 18% gray. It's halfway between white and black. We use this for either transmitted light or for reflective light. This is the thing that we use to... A gray card is equal parts of the 3 primary colors, both in transmitted and reflective light. It is nature. It's a combination of all that we naturally see in an image. Your camera is built on the assumption that everything you're taking a picture of is a combination of all these different colors, and that is 18% gray. When you take your pictures in to be printed at Walgreens and get them printed, every morning when they set up their printer, they take a picture of their gray card, and then they printed out, and then they match up the print on the monitor to what they've print in their hand to make sure that they're getting exactly what they see on the monitor. Our eyes are both our best friend and our worst enemy. Our eyes adapt to the environment very, very quickly, and we aren't even aware that this is happening. You look out there in the bright sun, and the pupils close down, and you see off in the bright sun detail in light-colored object, and then you look in the shade, and the pupils open up wide, and you can see detail in the shaded areas. The camera, our cameras have a very difficult time doing that. They can't handle this variation between light and dark back and forth. You need to tell the camera what's going on, because it doesn't have the ability without you telling it what is happening in this image. We have all different kinds of images and everything. You need to tell your camera what you're doing and what you want it to document what is important in your pictures. Daylight is your most common light source. We talk about quality, intensity, and color temperature, and it changes from the first thing in the morning till the last. Daylight changes constantly during the day. You measure it in quantity, intensity, and color temperature. And different color temperatures depending on pollutants in the air and clouds and other things that are going on. Type of light is evenness or quantity. Characteristics of light. The type of light is quantity and evenness. Is it evenly lit? Do you have a lot of it? Intensity, the amount. Quantity, how much light do you have? Or color temperature. We will talk about this, so you know what the color temperature, what the color of the light is.
All right, hang on. Let's go back. This one. You said type of light, quantity, and evenness, not quality and evenness. So let's redo that one.
Let's do it all of it,
Yeah.
all the way over. Characteristics of light. Type of light. Quantity.
Oh, you did it again. Quality. That's okay.
The characteristics of light. The characteristics of light. Type of light. The quantity of light.
Got it again.
Characteristics of light. The quality of light. Evenness. Is it evenly spread out over what you're taking a picture of or not? The intensity, the quantity of light, the amount. How much light do you have to work with? And the color temperature of light. The color of light.
That was perfect. All right.
Color balance. Here are illustrations showing you that the color of light can vary all over. And what you see through the camera is what the camera sees, and what it captures might be something totally different. You need to take charge of the camera and tell it to capture what you want to see and what you want it to capture. You make the choices. It's like a computer. Well, cameras and computers are very similar. The camera is a blindingly fast, stupid machine that you have to direct it to do what you want it to do. Here are examples of the same exact location at different times of the year and different times of the day, showing that how lighting situations can change. Electronic flash. Electronic flash unit is a gas-filled chamber. It's a portable light source. It's a tube with wires in it filled with gas that you heat up, and it produces light in milliseconds, somewhere between 5,000 and 6,000 degrees. Your flash unit can be adjusted. The duration can be adjusted from very, very short to a relatively long, but it's still in milliseconds. Tungsten light. Tungsten light is light created from heating up a ribbon of tungsten, make it glow, and produce light. Tungsten lights are terribly inefficient light sources. They produce a lot of heat and at the expense. Tungsten lighting is a common artificial light source. The light is produced by heating a tungsten wire inside of a vacuum to produce light. It produces a lot of heat, but it's a terribly efficient light source. It is used in homes and daylight settings in most homes. We are evolving away from this into LEDs, light emitting diode, to replace tungsten lights. Here are examples. This is what your camera does and what it captures when you set your camera on daylight. The picture on the left is a picture captured with expecting to be taking pictures of daylight, and you get this warm kind of orangey color. And then the one on the right is fluorescence, and fluorescence is a tube filled with gas that produces only cyan and magenta. There is no red. It's all blue and green, magenta light. Wrong. Illumination. Here's an example photograph showing tungsten versus fluorescent illumination. The image on the left is an image captured with the camera set for daylight in a tungsten environment. It's warm and looks orange in it. It does not look like what you are seeing when you're capturing this image. The camera captures something completely different. The picture on the right is a picture of a fluorescently lit environment. Again, this is not what we see, what our brain sees. This is what the camera captures. The light source in there is fluorescent tubes. They produce cyan light. It contains no red. We put in the red because we have a bias in our brain and we see this and we know it should be there. So we are not even aware that this is happening, and it just works that way. Fluorescent tube. Your brain quickly adapts to these fluorescent tubes, and puts in the red that you don't see. When I was working at the police department, we ran into a problem where we were printing pictures, and I got some complaints from some of our people that we were producing prints for, and they said, your pictures are off color. And I went and looked at them and took them outside and said they were right. And so what I ended up doing was figuring out that the city of Los Angeles was buying cheap, inexpensive Home Depot fluorescent tubes to put up in the ceilings, lights in the photo lab. Well, I had the authority, and I went and bought daylight fluorescent tubes for the entire photo lab, from the office all the way through from when you walked in the door until you walked out of the door, so that the lighting environment was daylight. So when you were looking at the pictures in the photo lab, they looked the same as you would see them out in daylight. Here's our illustration showing you some of the examples of the different colors of fluorescent tubes that are out there available. Metal halides, sodium vapor, and all of these lights are out there in the environment. Here in the classroom or in a large parking lot, you will see these different lamps lighting up the parking lot or something like that. They are very good. It almost looks like Christmas. They have different colors of illumination. They go to the low bidder for the lights, and they work beautifully and do the job of showing the streets, but they aren't worried about the colors. This is the lighting situation from hell. This is where you've got tungsten in the foreground in this fixture. You've got a fluorescent tube up in the ceiling and daylight off there through the window. You can balance one of the picture for one of these colors, but you can't balance it for all three of them. This is an impossibility. You need to be aware of what's going on here, and the easy solution to this one, which is not easy, is to change all of the light bulbs in there into daylight Kelvin temperature light bulbs. They make daylight fluorescence, and they make LEDs daylight to replace the tungsten lights in the light fixture. Here's another one of those situations where we have mixed lighting. We've got, it looks like it's Christmas there. They've got all kinds of different light sources, and this makes it very difficult. Laser. I use a laser in my classes to help me to point out good things and bad things from assignments or my students when they turn in their assignments. The light amplification by stimulated emission radiation produces a little point light source, and you can move around and show what's going on. But you can show where it begins and where it ends, but you can't show its travel. In order to show the path of the laser, you need to put something in its path. There's one of two solutions to this commonly out there now. And one is to take a piece of paper and go down the path of the laser and paint in the light. Leave the lens open for a long period and just move the white paper down the length of the laser light source and paint in the path. Or you get some smoke. There are vendors out there that produce a smoke that they can spray up and make this work so you can make this visible. When I was working very early in my career, I needed to take pictures in a clean environment with a laser. And I couldn't take anything in there with me, couldn't take any smoke or anything like that. And they wanted the picture of showing their new piece of equipment that used a laser. And so I needed to figure out a way to make the path of this laser visible without leaving anything behind or contaminating their environment. And I figured out and brought some dry ice to the job and some warm water, and I could produce some fog. And it came up and it made the path of the laser visible, and it disappeared up into the air vents, and they were very pleased with the picture. Photographs are a moment in time captured on light-sensitive material. What separates the professional from the amateur? The professional needs to produce pictures every time. I'm only as good as the last picture I took. I don't get work and get jobs unless I can produce top quality pictures that satisfy the wants and needs of the people who employ me. Tools of trade for the photographer. You have to have a light. You have to have light, daylight, electronic flash, whatever. You need a camera, a light-tight box with a hole in it. You have to have a means to capture those images and preserve them. And lifelong learning, because you're going to be learning, because this field is constantly changing, and it will continue to change for the rest of your life as it has for mine. If you have any questions, please feel free to contact me.